Hey everybody, we're looking at a page that's in your packet. It's in packet 4C, and we're looking at this pedigree, and we're going to answer the questions based on what we see here. First question, is the pedigree shown above consistent with the pattern you might expect for a sex-linked trait controlled by a recessive allele? Explain your answer. The second question says, male 12 could have inherited the trait, but by chance he did not. Explain why males 5 and 13 could not have inherited the trait. So what I've done here is I've taken this pedigree, and I have a copy of it right here. And the first individual that they're asking us to look at is male number 12. So what I thought we would do to determine whether or not we think this might be a sex-linked trait is let's try a hypothetical sex-linked trait and apply what we see for the parents of male number 12 to a Punnett square and see if it is consistent with being a sex-linked recessive trait. If we look at dad number 8 does not have the trait. So let's use as our hypothetical example male pattern baldness. We'll use an uppercase H as the superscript to denote a full head of hair, and we'll use a lowercase h to be the recessive sex-linked trait for male pattern baldness. Now, if dad does not have the trait, that means he has the healthy allele, which remember we're using an uppercase H for that. So this is representing dad number 8. Now over here we have mom number 9, who they're saying is a carrier. A half shaded in means carrier. So if she's a carrier, that means she's got the healthy full head of hair allele, but she has the bald allele also on her other X chromosome. Now if we complete the Punnett square to show what's possible for the offspring, let's start with the girls. The girls are on the left. So this girl, we would copy the XX and we would use the two uppercase H's for the superscript on that. So that's a girl that has no problem with baldness and is not a carrier. If we look at this next girl, in this case, we would have the healthy allele inherited from dad, but the bald allele inherited from mom. So that would be a carrier daughter. Now, this couple did not have a daughter, but what could be a possibility is a half shaded in circle as an offspring for this couple, if we're assuming that's a sex-linked recessive trait. Let's look at the boys. So the boys, we have an XY, and we're taking mom's healthy hair allele. So that's a boy that has no problem, which isn't that what we have going on with son number 12. And if we look at this, we have a boy that has inherited the bald allele from mom. So if this couple had another son, and this was a sex-linked recessive trait, then you would expect the other son perhaps to be bald. All right, so let's take a look at males 5 and 13, and let's look at their parents. So male number 5 is right here, and if we look at male number 5's parents, that's this couple. And if we look at male number 13, that's right here, and we look at his parents, they both have a dad with the trait and a mom that does not have the trait and is not a carrier either. So if we do a Punnett square to reflect that and then look at the offspring outcomes, then we can further decide whether or not this is indeed a sex-linked recessive trait. So this would be dad. So remember, dad has the trait for both male number 2 and male number 10. They both have it, so that means they have the lowercase h for the bald allele. Mom is not a carrier in both cases for number 1 and number 11. So that means mom has the healthy hair allele, which means uppercase H, uppercase H. If we take a look at the offspring, let's look at the girls first. The girls, this daughter inherits healthy allele from mom, but inherits from dad the bald allele, so that would be a carrier daughter, which we do see with daughter number 14. And if we look at this daughter, we have another carrier daughter, which again is consistent with daughter number 14. Let's look at the boys for the same family. This boy inherits the healthy hair allele from mom, and so does this boy. So none of the boys, if we have this allele combination for the parents, could ever have the issue of male pattern baldness or hemophilia or color blindness or whatever sex-linked recessive trait we're talking about. So far, both of these Punnett squares seem to match what we see in this pedigree. So what does that mean? It means this is consistent. So let's answer the question. It says, is the pedigree shown above consistent with the pattern you might expect for a sex-linked trait controlled by recessive allele? Explain your answer. And let's say the pedigree above is consistent with the pattern typically seen, and I probably should add here recessive. recessive sex-linked traits because we see females as carriers and males with the condition, and we could further explain that by using our Punnett squares here. This kind of supports the idea that it's a sex-linked trait. All right, so if we look at the next question, you may have to pause that to write that in your packet. Let's look at the next question. It says, applying concepts, male 12 could have inherited the trait, but by chance he did not. So male number 12, that would be this son, right? Because this son would have inherited the trait. So this couple has, if we're talking about their sons, half of the sons would have it, half of their sons would not have it. So this would be the bald son, and this would be the perfectly healthy son. Now let's look at males 5 and 13. If we look at males 5 and 13, both of them do not have it. And if we look at the outcome for the parents, so the parents, either set of parents, either the one I have circled here or the ones I have circled here, it's the same Punnett square. In both cases, you're going to have a 0 probability of having a son with the condition. Because why? Because they inherit their healthy allele. Their X chromosome comes from mom, and the healthy allele is associated with the X chromosome. So this son gets X from mom, this son gets X from mom. So how should we word that? Maybe write something like this. Male number 12 inherited his X allele with the healthy allele from his mother, so that's this. Both males 5 and 13 inherited their healthy X chromosome from their mom. So that explains why they do not have the trait. All right, so you may have to pause that to finish writing that down. Let's take a look at the next page, which looks like this. Interpret the data to answer each of the following questions. Write your answers in the spaces provided. Smile dimples are controlled by a dominant allele on a single gene. Whitney has smile dimples, but her husband Alberto and son Pedro do not. What is the chance that Whitney and Alberto's next child will have smile dimples? Draw a pedigree to show how you arrived at your answer. So let's put a pedigree because they're asking for that, but I think it's also going to be relevant to put in a Punnett square as well. So this will represent the parents. So we have Whitney and we have Alberto, and we have their son Pedro, and let's have their next child be a daughter this time. But let's fill in what the alleles must be, because what do we know about Whitney? We know she has smile dimples, and it does say that they're controlled by a dominant allele. So Whitney, if she's got the dimples, she has to have the dominant allele, but why don't we throw in the recessive allele for no dimples for Whitney just to see what happens. So let's call her a heterozygous. Oops, I hate that when that happens. All right, so she's heterozygous, and let's have Alberto. All we know about Alberto, it says her husband Alberto and son Pedro do not have smile dimples. So that means that he probably would be this. And if we complete the Punnett square to figure out what Pedro, which situation is Pedro, let's fill that in. So here we would have an uppercase D and a lowercase d. So that's a child with dimples. That would be the same thing here. Down here we're pulling from here and here. That's a child that does not have dimples. And then here and here goes in this box. So that's a child that doesn't have dimples. So what are we going to do? Let's fill in who has dimples. So mom has dimples, and Pedro does not. But let's have the daughter. So let's have this represent the daughter. So shade that in as having. Maybe we should use a darker color. How about we use maybe green instead? All right. Now let's answer the question also, which we could write this. The probability that Whitney's and Alberto's next child will have smile dimples is 50%. All right, let's look at the next question. And again, if you have to pause it to finish filling in your packet, you should do that. Although Janelle's blood is normal, her brother Randy has sickle cell disease. Janelle is worried about having a child with the disease. Janelle just found out that her husband Terrence has one allele for sickle cell disease. As their genetic counselor, determine Janelle and Terrence's chances of having a child with sickle cell disease. How would you explain the results of your analysis to the couple? All right, so let's make a Punnett square for Janelle and Terrence. Now, what do we know about Terrence? We know he has one allele for sickle cell. And you'll see different ways that geneticists fill in a Punnett square for sickle cell disease. If they have the one allele, then we would have to use an S for being that one allele for sickle cell, but I've seen different letters used to represent the healthy allele. And one of the letters I've seen used is an A, but really, quite frankly, it doesn't matter what letter you use, as long as you're saying one is the healthy allele and the other one is the sickle cell. Now, if Janelle, it's saying that she has a brother that has sickle cell disease, so that means it runs in her family. And she also could be this, the same as Terrence. So let's just throw that in as a hypothetical. Now, she could also be perfectly healthy. She could have the AA allele. We'll explore that in just a minute. But let's fill in the offspring. So here we have upper A. Here we have an A and an S. Here we have an A and an S. And here we have an S and an S. So this child right here, this one, has sickle cell. They have the disease. These outcomes here show that we have the sickle cell trait, we might call it, but they also will have that one allele for the sickle cell. And then we have this perfectly healthy child. Now, the other thing we have to consider is, what if Janelle is perfectly healthy? If she's perfectly healthy and does not have the allele for sickle cell, which, by the way, if her brother has it, we have to assume that she probably does too, then that would change things up. That means that this child, instead of being that, would be that. And this child, instead of being SS, would be AS. So if that was true about Janelle, what would we tell this couple about what's going to happen with their offspring? Well, in all cases, except for, I should say 50% of the cases, 50% of the cases, they would have the allele for sickle. So they would have what we might think of a sickle cell trait rather than the disease. And then we would have 50% chance of having perfectly healthy children. But because Janelle's brother has a condition, we have to kind of lean more towards the idea that it might be this. So let's kind of do worst case scenario here for this couple. The chance of Janelle and Terrence having a child with sickle cell disease is 25%. 50% chance of their children to have the trait, so that's these two, and 25% chance of a healthy child, so that's this child. Now, if you wanted to also throw in the idea that Janelle might also potentially be uppercase A, we can talk about that, but we would want to advise worst case scenario over best case scenario if you were in fact a geneticist who would talk about both situations. All right, let's look at question number 3. Janice's mother has type AB blood and her father has type O blood. What blood types could Janice have? Draw a Punnett square to explain your answer. Now, if mom has type AB blood, then her alleles would be uppercase I superscript A, uppercase I superscript B, and dad with type O blood, he would have the two recessive alleles for O, which we use the lowercase I to denote that. And if we fill in the Punnett square for what Janelle could be, or Janice rather, I'm sorry, Janice. So Janice, she could be this. She has that allele combination as an outcome here as well. And then in this part of the Punnett square, we show the heterozygous for B. So this is heterozygous A, and this is heterozygous B. That means she could be either type A or B blood. So take a moment to hit the pause button if you need some more time to write that down, and make sure you get everything written down. All right, good luck finishing this up. Again, fast forward or pause to the parts that you need to get again.